Welcome to the deep dive. Today we're jumping straight into supervised machine learning, and we're going to pull out the essentials on two big concepts: regression for predicting numbers, and support vector machines for drawing, well, the ultimate dividing line.
Absolutely. These are foundational, and they really set up different kinds of goals when you're building predictive models. With supervised learning, the very first question you have to ask is, what kind of output are we looking for?
Exactly. Is it a quantity? Like how much? Or is it a category? Like which one?
Right. If the output you're after is a discrete variable, a label like happy or sad for a song, that's classification. But if you need a continuous number, something on a scale, like, say, predicting the exact person months for a software project, that's regression.
Okay, so forecasting next week's stock price, that's regression. But figuring out if the stock will go up or down, that's classification. Got it. It really does hinge on the output you need.
Precisely. And focusing on those continuous outcomes, predicting those real numbers, that puts us squarely in the world of regression. The whole point is to learn some kind of function, right? So you can feed in features and get a precise number out based on the examples you trained it on.
Okay, let's start with maybe the most well-known one, linear regression. It's called a functional algorithm because the model itself is literally a math function, usually a straight line or maybe a flat plane if you've got more inputs.
Yep.
But when you look at a scatter plot, just a cloud of data points, how does the algorithm actually pick which line is the best one?
That's where the math is actually quite neat. The basic idea is that the algorithm searches for the line that minimizes the sum of the squared differences. So the distance between each actual data point and the line itself. You square those distances and add them all up.
Okay, why squared?
Well, squaring does two things. It makes all the errors positive, so undershoots and overshoots don't cancel out, and it penalizes larger errors more heavily. The thinking is the line represents the true relationship, and those deviations are just noise. So the best line is the one that slices through that noise with the least total squared error.
That makes sense. Filtering the chaos to find the signal. So how does it mathematically find that perfect line amongst all the possibilities?
It does that by calculating two key things that define the line. The coefficients, that's the slope, telling you how much the output changes for each unit change in an input feature, and the intercept, which is basically where the line crosses the vertical axis when all inputs are zero. Find those, and you've built your linear model.
Right. But wait, before we even try to build that model, shouldn't we check if the things we're using as inputs, the features, actually have anything to do with the output? That sounds like correlation.
Absolutely crucial, yes. If you try predicting house prices using, the number of squirrels in the park, your model's going nowhere. We use Pearson's correlation coefficient, often just called R, to measure the linear relationship between two variables.
R is great. It's so neat. It goes from -1 to +1. +1 means perfect positive link, one goes up, the other goes up. -1, perfect inverse link, one goes up, the other goes down. And 0, no straight line relationship at all.
Exactly.
We have the line, we have the prediction. How do we know if it's actually any good? Like, how far off are these predictions usually?
Good question. That brings us to error metrics. For regression, probably the most common one is root mean squared error, or RMSE. Think of it as the typical size of your prediction errors. It's like the standard deviation of the residuals, the differences between your predictions and the actual values. You want this number to be as small as possible.
Lower is better.
Makes sense.
So for that birth rate model, the RMSE was 3.77. How do we know if that's good or bad? 3.77 what births?
Yeah, 3.77 points on the birth rate scale. You judge it relative to the data itself. The average birth rate across all countries in that data set was about 31.66. So an RMSE of 3.77 means your predictions are typically off by less than 4 points compared to an average value over 30. That suggests the model actually has some decent predictive power. It's doing much better than just guessing the average every time.
Okay, better than guessing the average. Is there a metric that captures that specifically, like how much improvement our model gives us?
Yes, there is. That's the coefficient of determination, or R squared, 2022. This tells you what proportion of the total variation in the output, in this case, birth rate, is actually explained by your model's inputs. It's calculated as 1 minus the ratio of your model's squared errors compared to the squared errors you'd get by just always predicting the mean.
So it's like a percentage. And 22.27 means our model explains 70% of the why birth rates vary.
Exactly. You want to maximize 22, push it closer to 1 or 100%.
Okay, so that wraps up the basics of predicting a quantity with regression. Built the line, measure the fit, check the errors, but now, whoa, what if the goal isn't a number, but a clear decision, yes or no? This category or that one, that's a totally different game, right?
Which leads us, I think, to support vector machines. SVMs.
Right, we're shifting gears completely. We're moving from fitting a line through the data points to drawing a boundary between groups of data points. SVMs are primarily classification methods, though they can be adapted for regression too. Their main goal is to find the optimal separating hyperplane.
Hyperplane. Okay, that's the technical term for the boundary. Line in 2D, plane in 3D, something higher dimensional if needed. But what makes it optimal? Aren't there lots of ways to draw a line between two groups?
There are, but the SVM looks for the hyperplane that has the largest possible margin, the biggest distance to the nearest data point from either class. Think of it like drawing the widest possible road separating two neighborhoods. The wider the road, the safer the separation. Ah, I like that. The widest road, or the biggest buffer zone. It feels more robust. If your boundary line is scraping right up against a data point, you wouldn't be very confident about points near that boundary, right? A tiny nudge could flip the classification.
Exactly right. And the points that actually lie on the edge of this widest road, the ones that define where the boundary must go, those are the critical ones. They're called the support vectors.
So these are the data points closest to the dividing line, the
Yeah.
ones that are hardest to classify?
Precisely. They are the ones that support the hyperplane. All the other points, the ones deep inside their own territory, they actually don't influence where the optimal boundary ends up. It's only these edge cases, the support vectors, that matter for defining that maximum margin separator.
Okay, so the SVM focuses only on the tricky points right at the border. That's efficient. Like border guards setting the boundary line. Points way inside don't change where the border is.
That's a good analogy. And because it's defined this way, finding the optimal hyperplane becomes a constrained optimization problem. Maximize that margin width under the condition that all your training points are correctly classified.
Yeah.
Or mostly correctly in some variations.
Okay, sounds powerful for clear-cut cases, but what if the data is just messy? Like, imagine trying to separate red dots and blue dots, but they're all mixed together in the middle. You can't just draw a straight line through that, can you?
You often can't, not in the original space. And that's where one of the most, frankly, brilliant ideas in machine learning comes in. The kernel trick.
Ah, the famous kernel trick. I've heard of this. What's the core idea?
The core idea is transformation. If you can't separate the points with a line in your current dimension, maybe you can if you project them into a higher dimension. Imagine those mixed up red and blue dots on a flat sheet of paper. What if you could somehow lift them off the page into 3D space? Suddenly, you might be able to slice between them cleanly with a flat plane.
So you map the data to a higher dimensional space where it becomes linearly separable.
Exactly.
But calculating things in like 100 dimensions sounds computationally impossible.
It would be. And that's the trick part. We don't actually have to do the mapping and calculations in that high dimensional space. We use something called a kernel function. This function, often written as Blade6 JSHA, takes two original data points as input and calculates what their dot products would be if they were mapped to the higher dimension.
Whoa. So you get the benefit of the high dimensional separation without ever going there.
That's the magic. You can solve the optimization problem using just the kernel function values calculated from your original data points. It's computationally clever. Of course, choosing the right kernel and its parameters is important, and complex kernels can sometimes lead to overfitting the training data too perfectly.
That makes sense. It's a trade-off. But it sounds like whether we're doing linear regression or these fancy SVMs, none of it works well if the data going in is garbage, right?
You have to clean and prepare your data, check for features that are basically telling you the same thing. That's feature independence, where correlation analysis helps, understand if relationships are linear or more complex, and critically, figure out how to handle missing values. Ignoring this stuff is a recipe for disaster.
Right, garbage in, garbage out, as they say. But assuming you do that prep work well, the SVM approach seems really robust. It's not surprising it's used in some serious applications.
Definitely. SVMs have proven successful in areas like text categorization, think spam filters or topic sorting. Image classification, definitely. Bioinformatics uses them heavily for things like classifying proteins or even cancer types based on gene expression data, and even things like recognizing handwritten characters.
Why do they generalize so well to new data in these cases?
A key reason is that the decision boundary only depends on those support vectors, those tricky edge cases. The bulk of the data doesn't influence it. This tends to make the model less sensitive to the specific training set and better at handling new, unseen examples.
Okay, so let's try to synthesize this. We've covered regression for numbers, SVMs for categories. What's the big picture connection here?
I think the main connection is their reliance on optimization. Both are fundamentally about finding the best mathematical representation according to some objective. For linear regression, it's minimizing the squared errors, maximizing $2 you're optimizing the fit of a line or plane.
Mm-hmm.
For SVMs, it's maximizing that margin, that boundary width.
Yeah.
You're optimizing the separation. Both use mathematical optimization to find the best solution based on the data.
So they're powerful because they translate these prediction or classification goals into clear mathematical problems that we can solve to get quantifiable results, reliable predictions, robust classifications.
Exactly. And SVMs have that extra benefit in their optimization. The math involved, solving a quadratic program, guarantees you find the single best global solution.
Mm-hmm.
There's no risk of getting stuck in a suboptimal local minimum, which can happen with some other algorithms.
That's a really valuable property, knowing you found the best answer according to your criteria.